of working remote 3, active microwave remote sensing, ISPRS. I'm honored to introduce these webinars. Our working group started a series of webinars. So we invite 12 very valuable lecturers. Today is the first time. And I introduce you to Laurent. Laurent is president of Commission 3 of ISPRS. Laurent, can you give us some speech?
Okay, thank you. So, hello, everybody. Good morning, good afternoon, good evening, good night, maybe. My name is Laurent Polidori. I'm the president of ISPRS Technical Commission 3, Remote Sensing. And on behalf of ISPRS, it's my pleasure to introduce this webinar, which is in fact the first one of a series dedicated to radar remote sensing. Among the 12 working groups of our commission, active microwave remote sensing is the topic of working group 3, conducted by Junichi Susaki from Japan and his officers. It's a very relevant topic. Radar is not a recent technology. Just to give a few examples, here in Brazil, where I live, the first complete radar mosaic is 50 years old, 50 years old. Sentinel-1, which is probably the most widely used spaceborne radar, is 10 years old. And SAR interferometry, which is the topic today, has been implemented, I would say, about 30 years ago after the launch of IRS 1 and 2. So this means a long experience and many things to discuss about the operational potential of radar technologies. At the same time, there is always something new. For instance, the biomass satellite will be launched in a few weeks by ESA with a very low frequency radar, P-band, which is something new on board the satellite. And this means new research activities. So it's a very interesting topic for all these reasons. I would like to congratulate and thank Junichi and his working group for organizing this webinar series. And thanks also to the Student Consortium and its president, Lakshmi Thapa, for the support, as usual, for the organization and communication. If there are students in the room, you should join the Student Consortium, which is in fact the student association inside ISPRS. And I guess Lakshmi will probably copy the link for you in the chat. So I don't want to be long. It's now time for me to give the floor to Junichi, who will now present the webinar series and this first webinar and introduce our speaker, Michele Crosetto. So please, Junichi, the floor is yours. Thank you.
Yes, Lauren, thank you so much for your messages. First and foremost, I sincerely express my thanks to the Ms. Lakshmi, President of ISPRS Student Consortium. Thank you for so much your valuable support. And okay, now we are going to start first seminar. So please send your information or your name or affiliation country like that, and also your questions into the chat box. We'll expect very active discussions. Okay, as you know, Michael's bibliography is introduced to you. So to save the time, I don't go into the details, but Michael is a very popular scientist in these areas, and he is working at the CTTC in Spain. And one of his major activities, today's topics, he generated this kind of products to the Europe or to all over the world. That's why many of you are interested in this scenario, in this product. So Michael, can you start your presentations?
Yes, thank you very much for the introduction. Good afternoon to everybody. My presentation, as the title says, concerns interferometric SAR, which is an active remote sensing technique used to measure and monitor deformation. As said before, this technique has been developed in the last 30 years. Within the realm of remote sensing, certainly represents a success story because it is widely used by many researchers and in general in the academia. There are several companies, several private companies that are providing services using this technique. And in addition, as we will see during the presentation, SAR interferometry is also part of the Copernicus portfolio. Copernicus is the Earth observation component of the European Union space program, and we will speak about this later. We will speak about the European Ground Motion Service. Let's start with SAR interferometry, a brief introduction. To start, I would like to try to motivate the people why we are speaking about this technique, and I offer some reasons. First of all, SAR interferometry is a wide area coverage technique, which has...
I'm sorry, I have to interrupt you. You haven't shared your slides, I think.
Yeah, I can see the slide.
Okay. Oh yeah, it's working now. Thank
Oh,
you.
it's okay. Yes, it's okay.
It's everything okay.
Yeah, sorry to interrupt. Please go ahead.
No problem. No problem. So it is a wide area coverage, but at the same time is a relatively high spatial resolution. And this allows us to get a global overlook of a large area and to zoom up to individual structure and buildings. Then the technique is very sensitive to small deformation. In terms of velocity, we are in the region of 1 millimeter per year standard deviation. The techniques allows a systematic monitoring in space and time. It is rather highly automated. It has the capability to measure, say, in the past, in the sense that now in 2025, we have more than 40 years 35 years of data archives, so a lot of SAR imagery that can be used. So what happens measuring the past? When there is a problem, say in a city or in any location, we are able to come back up to 91, exploiting the archives of the European Space Agency. This is, of course, an unmatched capability. And by using SAR interferometry is in general possible to get a reduction of the amount of work that needs to be done in situ. Okay, these are in general the characteristics of the technique. I would like to introduce briefly the principle of working of the technique. We have a point on the ground, which is P. We pass once with a satellite, a SAR satellite, sending microwaves. This is the brown M satellite, which sends the microwaves, goes up to the point and come back, and we measure out of it the phase, which we call phi M. If the points undergoes a deformation, so moves from P to P1, there is, say, a subsidence in this area, we need to pass at least a second time, and this is the position S of the satellite in green, who sends the microwaves, and again measure a phase, phi S. Now, if the position S and M coincide in space, the difference of the two phases observed by the two satellites is directly related to movement or deformation. This is not very common situation. More in general, the positions S and M do not coincide in space. And so there are in fact two components related to the same phase, which is the difference of the phases. One component is related to the topography of the observed scene, and the other component is related to the displacement or movement of the scene. This is not very useful because we have one observation, which is the interferometric phase, which is the difference of these two phases. And this observation is related to unknowns. We cannot resolve this. But there is a small trick. If we know the topography of the scene, then we can simulate the topographic component. We call it phi topo simulated. And we can subtract this component to the original interferometric phase, obtaining a differential interferometric phase, which is again only related to movement. This is really the principle of functioning. In reality, there are other components, but the question is the same. So the differential interferometric phase, which is the difference of the interferometric phase minus the simulated topography, is related for sure with the movement or deformation of the area. The atmospheric component, because our microwaves cross ionosphere and troposphere and back to the sensor. So there is an influence of the characteristic of the atmosphere on the phase. There is a residual topographic component, which is related to the operation we have mentioned at the beginning of this slide. We say we simulate the topography, but by simulating, we for sure generate some errors that we take into account with this component called phi-res topography, residual topography. And then there is always a component of the phase related to noise. This is more or less the global picture of SAR interferometry. We have to say that the first equation can be used in practice in some practical cases, like the one I'm going to show you, where we can neglect the atmospheric component because we are in, for instance, in very reduced areas. We can neglect the residual topography with respect to the deformation. We neglect the noise. And this is exactly what happens in this example, which is an ortho image on the background with on top of it the differential interferometric phase, which is color coded. The blue colors are around 0 deformation up to 47 millimeter of deformation. This is an old interferogram coming from the ERS mission, but with this simple interferogram, we are able to highlight deformation, which you can see in yellow to red, that are related to underground mining activity. This interferogram was observed through 35 days. This is a special case where we get very useful information by only 2 satellites, by only 2 acquisitions. In the general case, we have this second equation with different components. In order to estimate all these different components, we need many acquisitions over the same area. So the techniques, the more advanced technique, do not use only 2 acquisition, 2 images, but they use many of them. For instance, 20, 25, or much more. And with this redundancy of observation, it is possible to separate the contribution of the movement or deformation from the atmospheric contribution, from the residual topographic component, and from the noise. In this way, we are able to estimate the deformation of the area observed. I am not going in any details related to the processing needed to do this. We just jump directly to what are the typical products of SAR interferometry. The first product is the deformation velocity map. It is the linear deformation velocity estimated over the observed period, where I have my satellite acquisitions. It's called also average annual displacement rates or something like this. We get 1 velocity value per each measured point. We will come later on this. Usually the velocity is expressed in millimeter or centimeter per year because we are sensitive to rather small deformations. Okay? This is the main product of SAR interferometry. This is an example. This is a deformation velocity map of the metropolitan area of Barcelona. In green are the observed point, the observed velocity that are around zero, so stable area, but there are several locations where there are deformation in yellow to red, and some deformation going in blue. What does it mean? Let's have a look closely to the area of the airport and port of Barcelona. You see several areas. As said, the scale on the bottom, the yellow to reddish colors means that there are movement away from the satellite. Why the violet to blue colors are movements toward the satellite. So we have typically in red all the subsidence, so the going down of the terrain, and the uplift are depicted in blue. This is an example of deformation velocity. The second product, very important, is given by the deformation time series. They describe the temporal evolution of the deformation. The time series is estimated in correspondence to any of the acquisition used during the observed period. Okay. There is one time series per each measured point. These are typically expressed in millimeter or centimeter. Of course, this is a potentially very interesting product because the first one was only velocity, only one value, one rate over the entire period. In this case, like in this example, we have the complete description of the temporal evolution of the formation. In this specific example, you can see that there is a first period where the terrain is basically stable. Then starts a deformation which is rather linear over time. In some moment, it stops. There is a small recover of the deformation and then again stable. This example is an example of deformation due to underground water extraction. In this case was illegal water extraction. And of course, through the information of the time series, we can estimate very well the start of the pumping activity, the end of the pumping activity, and the effect of this pumping activity on the terrain. So from the application viewpoint, of course, the time series are very rich, very important, and very informative. Now, let's jump directly. This was just a short introduction of SAR interferometry. Let's jump directly to the ground motion service. What is this ground motion service? The goal of this service, called EGMS, is to provide consistent, updated, standardized, and reliable information related to natural and anthropogenic ground motion over Europe. Okay, so regardless any border, any difference, in a uniform way, we look at the deformation of Europe. This represents so far the most important SAR interferometric project ever conceived worldwide. What are the data used for this service? The data are Sentinel-1A and 1B, and soon Sentinel-1C from the European Union Copernicus program. These satellites carry out, of course, synthetic aperture radar sensors. The data are acquired when Sentinel-1 and B were working together. There was an acquisition, at least one acquisition every 6 days for both geometry of the acquisition. The geometry of acquisition are so-called ascending and descending geometry. Now, in this moment, and since December 20, 21, we have one acquisition of 12 days because Sentinel-B stopped its activity. But we are waiting Sentinel-C, which is already in orbit, is in this moment in the commissioning phase. The ground motion service has data available since 2014 and started, in fact, to deliver deformation starting from 2015. This is the coverage over Europe, just to have an idea. With the 2 satellites, you can see that in any place in Europe, in the south of Europe, you have at least 2 acquisitions per week. While when you move toward the north, in Scandinavia, Finno-Scandia, etc., you get much more acquisition, up to 7-8 acquisition per week. All these data are used in the Copernicus. This is the coverage of the service. Is including a big part of Europe. Unfortunately, there is no Switzerland, and there are not some of the Balkan countries. The rest of the country are covered. Is in fact the European Union plus UK plus Norway and Iceland. So are the 27 states of European Union plus 3 states. This is the coverage. What is the content of this ground motion service? It includes 3 types of products, which are called basic, calibrated, and ortho. What is a basic product? The basic products includes deformation maps and deformation time series measured along the radar line of sight. This is the line that connects the sensor to the point on the ground. These data are delivered for individual and consistent frames that are the frames of the original SAR data. The measurements are relative, so they are referred to a reference point, 1 per each frame, okay? And the processing is performed at full SAR resolution. The footprint of Sentinel-1 is 4 meters times 14 meters. This is an example close to Barcelona. Again, you have in green the estimated deformations. You have some subsidence, some uplift, etc., and very important, there is a point which is chosen by the processing team, which is the reference for the measurement. This is the basic product. Let's see what's the calibrated product. In the calibrated product, the mosaic products are the basic products are mosaiced, so are put all together in a seamless way. And much more important, the deformation maps, the deformation measurements coming from interferometry are combined with GNSS observations, okay? In this case, is the GNSS network, the GNSS information, which provides the backbone for the deformation of interferometry. So there is not, in this case, a single reference point. The reference is provided by GNSS. The deformations still refer to the radar line of sight and are coming from data at full resolution. This is a plot of the calibrated products over mainly North Europe. You can recognize that at global scale, everything is stable. So European is stable, but you can recognize in the north, in the Finno-Scandia, a clear blue color, which means a clear uplift. This is the post-glacial rebound of this area, which is still going on from the last glacial era. This information can be captured, is captured basically by the GNSS, okay? we have together interferometry and GNSS, and the deformation at very long scale, like this one of Finoscandia, are captured by GNSS. I am showing maps with colors. The colors typically refer to deformation velocity, but for each point, with each measurement point, we have the complete time series of observation. So this is an extract of one of the files, one of the outputs of the service. You have a point with an identification. You have the coordinates of these points, longitude, latitude, east, north, elevation. You have the velocity, and you have the entire time series of deformation related to each point. So each point is in one row, in one line. And this is just a plot of one of these time series with, in this case, a very linear deformation over time. Let's see the last product. The last product is the so-called ortho product. In this case, the product includes two main deformation components. They are horizontal east-west and vertical up and down component. We have said that the basic and the calibrated products show deformation in the radar line of sight. They are monodimensional in the direction that connects the sensor to the point on the ground. In this case, we make a nice step forward, very useful. We have for each point two components of the deformation. I repeat, the east-west horizontal component and the up and down vertical component. Unfortunately, we are not able to derive the third component, which is the horizontal north-south component. This is because we are using polar orbit satellite, and we are basically blind to this type of deformation. This is very nice. So in the other products, we get just one component. Here we get two components. Of course, there is a price to be paid for this. And the price is that this is possible only at coarse resolution, not these 4 by 14 points in every place where there is a good response. In this case, we speak about pixel size of pixel footprint of 100 by 100 meter, 1 hectare. Okay, and this is because to derive the two deformation, we need acquisition from both ascending and descending over exactly the same point. Okay, so we need slightly coarser resolution with respect to the other products. This is the ortho product at European scale. On the left, there is the up and down vertical that we have commented already with the post-glacial rebound in North Europe. And then there is the east-west component, which a very strong signal in Iceland and an even stronger signal in Greece, and especially in the Greece islands. Okay, in this case is a east-west deformation of this area. Again, this information is basically captured by GNSS. So to summarize, the entire workflow of EGMS is we start with Sentinel-1 stacks of images. We do a processing, which is persistent scatter and distributed scatter processing. We generate EGMS basic product. By calibration, the calibration is based on GNSS velocity model. We estimate the EGMS calibrated. And by resampling and calculation of the two components, we generate the EGMS ortho. Accessibility of the data. Everything mentioned so far is available is available at this link. Can be, if you want to check this information online, you can even with your mobile type this address, and you will have access to the so-called EGMS Explorer. The EGMS Explorer is something like this. You have all Europe, and you have a color scale, a toolbar, etc., to do basically visualization, and then there are other tools always available in this service to download the data. Right? I have an important warning here. When you visualize for the first time EGMS, in fact, when you visualize these explorers, you will always receive as an entry the data from the ortho product. The data from the ortho product are light because they are every 100 by 100 meter. So they are light to be managed for the visualization. But remember that in the location where you can have interest, so in the area of interest, you have available always the basic, the calibrated, and the ortho product. I say this because also in the publications, the great majority of the people use the ortho product. But for some application, it is very useful to exploit the full resolution of this data. I would like just to show some example of results. The first concerns the Port of Barcelona. This is just a plot with the browser. You have the points. I forgot to mention before, when you see here, you see in colors are the measured points, and in the background, you can see that there is an ortho image, okay? You can appreciate that the coverage of the colored points is rather uniform on the top of this image, but on the bottom, there are a lot of places where there are no these points. These are areas where the data, the interferometric data, are not good enough to derive deformation estimates. So in low coherence areas, these are typically the cultivated areas, the forested area, etc., we have much less density of measurement than the urban area as it is shown in this map. So this is the velocity map in color. We can choose this area, and we can plot automatically the time series. The time series in this case is a time series which is the average of 370 points, and you have the time series starting from 2015 up to 2021 in this case, with 30 millimeter of deformation maximum. Let's see another example with much more deformation. This is a dike which protects the port from the sea. In this case, we have 210 points and a much bigger deformation, up to 12 centimeters in the same period of time. This is as simple as I am telling you. You zoom in your area of interest and you visualize the data. You can choose your area. You plot the time series. Everything is done with the EGMS Explorer. Just another example to show a variety of examples. This is in south of Poland, an area very active with many deformations. This is a coal area, one of the most important coal area in Europe. The coal is extracted from underground, and the underground extraction activity generates an important impact on in the surface. By the way, this is with the ortho. The ortho, this is the up and down deformation. You see that most of the area are going down because they are yellow to red, but there are important areas that are undergoing uplift. This is related to the water table of the mines. These are abandoned mines where once abandoned, the water table goes up and provocates uplift. And this is the east-west component. Just to show, of course, most of the European sites are rather boring because they are green, there are no deformation, but there are special places in Europe, for instance, the Etna volcano, which are very active and have a very colorful deformation area. This is the ascending deformation area. There are, this is the Etna area. There are the major faults of this area, and there is a star, a white star, which indicates the position of one earthquake. This is ascending, this is descending data, okay? They are not so easy to be interpreted, but in this case, with the up and down of the ortho product, you can see here the vertical movement related to this volcano. It is, of course, a complex body with a very complex deformation, but these are the estimated up and down, and this is the estimated east to west component, right? Everything is available to everybody through the Explorer, as said. In order to finish, I would like to mention that there is the need to develop some analysis tools. Okay, we have plenty of data. We have huge data sets. In this moment, I don't remember how many points, measured points there are over Europe, but they are on the order of billion of points, right? So very huge data set. So there is the need to develop automatic, if possible, automatic or semi-automatic tools to analyze the data. And I will just show one very simple example in order to give an idea. We call it the active deformation area. In this case, is out of the entire data set of measuring points, we basically threshold the velocity in order to detect only the active area, and we impose to have a cluster of these points. We are not looking at single points, rather a cluster, and this cluster above a given threshold provide the so-called active deformation areas. And the active deformation area are okay, there is a quality index which can be associated to this product, but what is important that in this example, on the right, you have the typical results coming from EGMS in terms of velocity, and on the other side, you have the very simplified map, which is a vector map of the extracted area with activity of deformation. And this area can be classified according to their velocity. Okay, so the idea is that this is a simple example. I choose not to put other example, not to make a longer presentation, but the message is that in many cases, very huge data set of data are overwhelming particular type of users. There are some type of users that prefer to receive the example that you see here on the left, and you say, this is the vector map of the active area in your area of interest. okay? We have other activities that try to automatically classify this cluster of data. So automatically give a label, for instance, landslide, for instance, subsidence, uplift, sinkhole, etc. And this is another attempt to simplify the data for users, for instance, that are interested in monitoring an entire country. For instance, Spain, they want to have, for instance, the top 500 phenomena, deformation phenomena that occur, because they prefer to prioritize the actions on such top 500 cases than receiving hundreds of millions of points, right? This is more or less the idea. And to finish, this ground motion ADA is a web page where we have published all the active deformation area of, let's say, Central and South Europe. These are available on this web page. From my side, this is all. So thank you very much for your attention.
Michael, thank you so much for your valuable presentations and lectures. So, first of all, as you may know, one question is coming from our audience, Mr. Diego Taroda. His question is there indication of which one is there indication of which one is a reference point for each frame? Can you catch a point? Is there indication of which one is a reference point for each frame?
Yes, you know, for each
Okay.
for each measurement point, you have the indication of the corresponding frame, because when you download the data, the data are downloaded by burst of images. The bursts are like sub-images of a given frame. So a frame is divided in 27 bursts, and you download an entire burst when you want to analyze a given area. So you have always the reference, which is the original frame. Yes.
Yes. Okay, we have a second question. But before that, I have a similar question. That you mentioned that you have three products: basic products, calibrated products, and also products. So calibrated products are calibrated based on the reference GNSS network. So it means that there is a different system and calibrations.
The calibration is done in this way. From they use, say, most of the permanent station, GNSS permanent stations, right? We are speaking about 5,000, 6,000 or 7,000 permanent station in Europe. They estimate from this permanent station a grid, which is every 50 kilometers, a grid of the velocity. And this is called the GNSS model, okay? Then the information of this model is fused together with the interferometric data, providing a unique product, which is this calibrated product. And then the ortho product is also using calibrated data.
Okay, thank you. And the next one, can you check the chat? There is a second question that from David Ludwigana. On slide 37, you showed us a graph where you could see a downward trend. My question is this: why are these gaps? You can clearly see the line going down. Yeah, can you go to the slide 37? And you can clearly see the line going down over the month, but there are two gaps. Could you explain why? Yeah, 37th.
I don't understand it to which. to which slide?
Okay.
37, 37,
37, yeah,
sorry.
37, 37. Maybe yes.
Okay, sorry, here.
Yeah, exactly this
Yes,
one.
yes, that one, yes, yes. So his point is that there are two gaps. Can you explain the two gaps, why it occurs? Is this lacking of the observations?
Yeah, for sure there is either lacking observation or maybe there
Yes,
were
yes.
observations that had some problems. But if in fact we are speaking about October, September, October 2015, something happened with the data. I don't remember, but yes, there were no available data, or the processing team decided to not to use this data. I don't know exactly what is the reason, but yes,
Okay,
is a lack
okay.
is a lack of.
Okay, thank you for your reply. And the third question is like this. So the EGMS product will have a new version that updates the dataset. Do you know what novelties they will present? I mean, what is the advantage of the new product of the EGMS? He mentioned that the EGMS product will have a new version. I'm not sure.
New?
Okay. Can you check the chat box? This is from Alex Alonso. Okay. Okay, I repeat that, read it again. The EGMS product will have a new version that updates the dataset. Do you know what novelties they will present? You're not sure so much. Okay.
Yeah, I'm sorry, I don't understand completely the question, but we don't expect in the short period a very big difference, very new products from the EGMS. The EGM, they will keep going. I forgot to mention
Okay,
that.
okay, keep on going. And next question, can you check this one from Jeffrey Dias? Can SAR be used to analyze loss of soils or erosion? Can SAR be used to analyze loss of soils or erosions?
Only partially, because when there is soil erosion and we speak about very important volume of erosions, typically this is associated with the loss of coherence of the data. Okay, so if there is strong erosion, we lose our measurement point. So this is a limitation.
Yes, yes, yes. Yeah, I understand that if we can observe a significant displacement due to the soil erosion, yeah, we can observe, but yeah, if not, it may be difficult. Okay, the next question. Michael, can you check the chat box by yourself on your laptop?
I don't know how to do it. Sorry, I'm trying.
Okay.
I can read it if that is okay. I can read it if.
Okay, please read it. Yes.
Yeah. So far we have finished the question up to Jeffrey. So I'm going to. So Carlos has written it in Spanish. I'm sorry. Can you please write it in English because we don't know how to read it. So I'm following the question in the Q&A session first because it was written earlier. So it says, thank you for the presentation. I have a question regarding SAO L-band data. Have you worked with L-band data and encountered challenges such as long baselines and phase ramps?
In general, the INSAR community is also working with L-band data. We have a limited experience so far, but of course there are important improvement in terms of coverage, okay, in terms of coherence of the data, because you can have a much more measurement points over cultivated and forested area. In the EGMS, of course, this is not used because there is no availability of data in this moment, but at least Copernicus data, okay? But probably in the near future, the L band will be taken into consideration, considering the new missions. NISAR and ROS-L.
Thank you. So the next question says, can we see the deformation in agricultural area unlike urban areas? Does Sentinel-1 sensitive to deformation in agricultural area?
Yeah, in the agricultural area, like in the forested area, depends, we call that the technique is opportunistic. We send these microwaves, the microwaves are sent everywhere, over urban area, over peri-urban area, over vegetated, etc. What counts is the response of the terrain, okay? Yeah, so if the terrain has enough good response, we can estimate the deformation, and this can happen also in cultivated area, but depends really from case to case, if there are enough measurement points.
So the next question says, did you consider the orbit direction to interpret vertical changes? I can read it again. So it says, did you consider the orbit direction to interpret vertical changes?
Well, the orbits are part of the processing. Of course, we use the orbital information, but we discard the information related to north-south because we are unable to estimate this component.
Thank you. So the next question says, may I ask which software you used for data processing? For example, IFGS generation and TS in SAR processing?
Well, I don't know if the question is related to our group. In CTTC we have our own software that we have written in the last 25 years. But related to the EGMS, EGMS is in this moment produced by a consortium of companies specialized in interferometry, and each of the 4 companies uses its own software. So one company is, for instance, Tre Altamira. Tre Altamira has his own software and runs and covers some countries of Europe. Then there are other companies doing the same, and all together make a European coverage.
So the next question is, so we have 5 more minutes. So the next, we will try to take as many as we can. So the next question says, in cities where there are parks, vegetation areas, and areas adjacent to rivers, is it advisable to leave these areas aside so as not to introduce decorrelation?
Yes, there can be a technique, there can be an approach to mask the areas like a river or very, very dense vegetated or forested areas where you expect basically nothing, only noise. You can mask to have a better results. Yes.
So the next question is, I'm asking the question by Laura now because I've taken already 2 questions by Divya. So it says, by Laura, hello, thank you for the wonderful presentation. I wanted to ask, is the atmospheric phase screen estimation and removal performed for the basic product or directly for the calibrated product together with the ETRF 2000 connected?
No, the atmospheric estimation is done at the beginning over the basic products. Yeah.
Thank you. So the next question says, will you consider temporarily coherent scatterers in future version of EGMS?
Yes, this is a good idea. It was already mentioned in some of the meeting, etc. In this moment, it is not part of the production and will be not in the short term. But of course, is an interesting evolution. The only point that we are quite conservative in using new approaches, etc., because everything must be very well balanced with the capability to process the data. Okay? Already now, with the rather simplified processing, it takes months and months to do the processing. And in fact, the update of the products is once per year in this moment. If we are going to complicate the processing, of course, everything is going to be more time consuming.
So maybe two more questions. So the second last one says, can you please elaborate more about up and down component in ortho products? Is it one-dimensional measurement?
Yes, it is the vertical component of the deformation. So the deformation along the vertical, so can be up or down. In any point, we have at least two observations, one from ascending and one from descending. So we have two equations we can write, and we have two unknown that are the vertical up and down and the horizontal east to west.
So I think we should consider this one as last because we just have 2 more minutes and Professor Junichi might want to give a closing remark. So it says, I saw that the second generation of data has recently been uploaded to the EGMS website. Is it possible to download the first generation data from 2015 to 2021?
Yes, it is possible. Now I don't remember how it is. If you have to write to the help desk of the program, but either it is available in the browser, in the Explorer, or you have to request the data.
Sorry, I think it's a very minor remark, so I wanted to make it before passing it to Professor Junichi. It says should not be said SAR imagery, rather radar imagery. He's saying like, should not we be calling it as SAR imagery instead of radar imagery?
Yes, I use more or less as a synonym, but the more appropriate is a synthetic aperture radar imagery. Yes.
So thank you so much. If there are any, I've tried to take as most as possible. If there are 1 or 2 questions that might have left, please, I think Michael has already shared his email. Feel free to contact him. Considering the time limitation, I would like to pass it over to Junichi and want to say thank you to everyone for their active engagement. And thank you for the great presentation to Michael as well. Over to you, Professor Junichi.
Okay, thank you, Lakshmi, for the coordination. Also, thank you, participants, for active discussions. I appreciate your participations. So now it's time to close this lecture. And finally, we express our thanks to the Michael, Crosetto. Thank you for your presentations. Today's presentation is very valuable. Okay.
Thank you.
today is our first lecture. The next month, 12th of March, on the second Wednesday, we'll have a second webinar. Okay, please join us again. Okay, see you again next month. Okay, thank you for joining us. We'll see you next month. Bye-bye.
Bye. Bye-bye.
Bye, everyone.
Bye. Bye-bye.